All right, I'd like to do a couple more examples of related rates problems. So the first problem will be number 45 from the textbook. And in this problem I have a floor and a wall, and there's a ladder leaning against the wall. And the ladder is 26 feet long, and the ladder begins to slide down away from the wall. So the bottom begins to slide to the left, and that's going to mean that the top is going to slide down. So at some later time, maybe the ladder is sitting like this. And eventually the top of the ladder will hit the floor. But the question will be, if I know that the lower end is being moved away from the wall at a rate of 5 feet per second, how fast is the height of the top changing? And so this will be a negative rate because the top is moving downward. And we want to know how fast it's changing when the lower end is 10 feet from the wall. Okay, so to do this problem, I'm going to need to figure out a relationship between the position of the bottom of the ladder, so let's call that coordinate x, and the position of the top of the ladder. Let's call that y. Okay, I need a relationship between x and y, and I'm going to assume that this is a right angle down here in the corner where the floor meets the wall. So that gives me a right triangle, and the base is x, the height is y, and the hypotenuse is 26 feet. So I know from the Pythagorean theorem that on a right triangle, x squared plus y squared, the sum of the squares of the two sides is equal to the square of the hypotenuse, 26 feet, that quantity squared. Okay, so now I can get a relationship between x and y. And what I could do is solve this for y in terms of x. So if I did that, I would say subtract x squared from both sides. So y squared is 26 feet squared minus x squared. And then I know x and y are both positive, so I can take the square root and just not worry about the plus or minus. So I could say y is square root of 26 feet squared minus x squared. So that gets me a relationship between y as a function of x. So I'm told then that the x coordinate, the bottom of the ladder, is moving away from the wall at a speed of 5 feet per second. So that would be described by dx dt. So that's 5 feet per second. And at the time I'm interested in, the bottom of the ladder is going to be 10 feet away from the wall. So let me work out my derivative of my relationship equation. So I'm going to take this equation and find its derivative. I could have started with my original equation and taken a derivative of that. I would use implicit differentiation, and that looks like it might be even a little bit easier because this equation has that square root, which is going to make the derivative a bit more annoying. So I think I'm going to go back to the original relationship between the two quantities and use that as the equation that I'll use for my derivative. So I want to differentiate the left-hand side and differentiate the right-hand side. And remember to use the chain rule because both x and y are changing with time, so they're both functions of t. Okay, so on the left-hand side, I've got x squared, so the derivative of that will be 2 times x to the first power times dx dt. Plus, now a derivative of y squared will be 2 times y times dy dt. And that will be equal to the derivative of 26 feet squared. Well, that's just a constant, so the derivative of that's going to be 0. Okay, so now I can plug in what I know. I know that dx dt is 5 feet per second. At the time I'm interested in, the bottom of the ladder is 10 feet from the wall, and that's the x value, so x will be 10 feet. And I want to know dy dt. That's the quantity I'm trying to figure out. But that leaves this y value. as something I don't know yet. So what I need to do is quickly find out what the y value would be at the time when the x value is 10 feet. So to do that, I'll just draw a little right triangle. And I know the hypotenuse is always going to be 26. And the bottom is going to be 10 because the base of the ladder is 10 feet from the wall. And this is going to be my y. So I can do a quick Pythagorean theorem to calculate what y is. I know 10 squared plus y squared will be 26 squared. So y squared is 26 squared minus 10 squared. And so y squared will be 576. And so y is the square root of that, which is 24. Okay, so now I know that my y is 24 feet at the point where x is 10 feet. So now I can put all of that into the calculator. On the first term, 2 times 10 times 5 is 100. And the units will be, I've got 2 units of feet, so feet squared over seconds, plus 2 times 24 is 48 feet times dy dt, and that's all equal to 0. So I want to solve this for dy dt. So I'll subtract my 100 feet per second squared, feet squared per second from both sides. 48 feet dy dt is negative 100 feet per second, feet squared per second. And then I'll divide both sides by 48 feet. So my end result will be dy dt will be negative 100 divided by 48. And the units on that will be, on the right hand side I had feet squared per second, and then I'm dividing by 48 feet, so it'll be feet per second. So I can write that as dy dt is equal to negative 2.083 feet per second. So that tells me how fast the top of the ladder is moving down the wall, and it's negative because it's going down, at the point where the ladder is 10 feet, the base of the ladder is 10 feet from the wall. All right, let's do the second example, and this will be problem 35 from the book. And this example gives us a revenue function and a cost function, and they both depend on a quantity x. So the revenue function is given by 280x minus 0.4x squared. The cost function is given by 5,000 plus 0.6x squared. And so our profit function will be given by the revenue minus the cost. So 280x minus 0.4x squared minus the cost function, 5,000 minus, because of that minus sign, 0.6x squared. So my profit function will be, let me put the constant term first, negative 5,000, and then the term with the x, so plus 280x, and then I'll combine the two terms with x squared. So minus 0.4 and minus 0.6 is minus 1x squared. So there's our profit function. And then we're told that dx dt is 300 units per day. And the point we're interested in is the point where x is 200. Okay, so that's our initial setup. Okay, let's start looking at this revenue function. And the first thing I want to notice is the revenue is a combination of a term multiplied by x and a term multiplied by x squared, and it's going to have some value in something like dollars or some unit of currency. So the units on x would be units, And I'm not going to need to carry that around. So this units per day figure on the dx dt, I'm not going to carry that through the equations. I'm just going to use the number 300 for dx dt and the number 200 for x, and assume that the revenue, cost, and profit functions are built so that they're giving the proper units when those things are plugged in. Okay, so I want to find the rate of change of revenue with respect to time. So dr dt, and that would be the derivative with respect to time of the left-hand side of the revenue equation. So if I differentiate the right-hand side using implicit differentiation and keeping in mind that x is a function of t. So it would be 280 times dx dt, and then negative 0.4 x to the first power, 2 times x to the first power times dx dt. All right, and now I can put in the values that I know. I know dx dt is 300, and that appears in two places. And I know that x is 200. So if I put that into the calculator, the 280 times 300 is 84,000. And then negative 0.4 times 2 times 200 times 300 is negative 48,000. And so when I subtract, I get 36,000. So that's a positive number, so my revenue is increasing at a rate of 36,000 whatever dollars or whatever currency things, and I'm assuming that's going to be per day. Okay, let's move on and work on the rate of change of the cost as a function of time. So that will be dc dt, and I'll get that by differentiating the cost function. The left-hand side derivative is just dc dt. The derivative of the right-hand side, the 5,000 is a constant, so its derivative will be 0. Now I've got the plus 0.6, and the derivative of x squared will be 2 times x to the first power times dx dt. Now I can put in my 300 for dx dt and 200 for x, and so dc dt, if I put that all into the calculator, I get 72,000 per day, and those are probably dollars. Okay, and last, I want to look at this profit value, which is described by this function. And I could look at my revenue and my cost and say that since profit is always revenue minus cost, the rate of change of profit should be the rate of change of revenue minus the rate of change of cost. So I could assume that, and that would mean my dr minus dc dt, and that would come from taking the function p is r minus c and differentiating both sides implicitly. So I could do it that way, and then I could use the values I had from before, which was 36,000 minus 72,000, and that would give me a rate of change of profit of negative 36,000 per day. Or I could do what I've done before and take my profit function and differentiate both sides implicitly. So I could do dp dt, and then using this right-hand side, so the negative 5,000, the derivative of that will be 0. The 280x, the derivative of that will be plus 280 dx dt. And then minus x squared, the derivative of that is minus 2x dx dt. And then I can put in the values I know. So this will be 280 times 300 dx dt minus 2 times 200, which is x, times 300 which is dx dt, and that would give me 84,000 minus 120,000, and that would be negative 36,000 per day. So either way I do the calculation, I end up with the same rate of change of profit with respect to time.